This video presents the adiabatic heating effects during high strain rate tests. These investigations are located in the Subproject C2 Mechanical Properties in the frame of the Collaborative Research Center SFB 761 Steel ab initio. But first of all, what does adiabatic heating mean? The deformation of a metal leads to the fact that energy is released, which is a majority, approximately 90%, converted into heat. This is called dissipation. Due to the Euro NCAP crash test, a car is crashed with a velocity of 64.4 km per hour. In this case, the strain rate at the crash box is approximately 200 per second, which is 4 magnitudes higher than in the quasi-static tensile test. The cold-rolled material is delivered by IBF. Here at the Institute of Ferrous Metallurgy, the samples out of ultra-high-strength steels are cut by wire erosion or by water jet cutting. The samples are fabricated with a pressure of 3000 bar.
After cutting, the samples are recrystallized in a salt bath. To obtain accurate testing data, the preparation of the specimen has to be carried out carefully. Measuring the characteristic values, for example thickness, width, gauge length. Cleaning and preparing the surface for the attachment of strain gauges for the force measurement in the section of the specimen where only elastic deformation occurs. Firstly, the sample is sprayed in black and afterwards the shoulders are painted in white. This color contrast is necessary because the strain is measured with an optoelectronic extensometer directly on the sample. The high strain rate tests are performed on the servo-hydraulic high strain rate testing machine according to SFB 1230. The tests are performed to characterize the material's behavior under crash conditions, especially for the automotive industry.
In the context of material testing, the rise in temperature affects the results. Hence, at the Institute of Ferrous Metallurgy, the sample warming during testing is measured with a high-speed thermographic camera. In contrast to quasi-static tensile tests with high testing velocities, the heat cannot be transferred to the environment any longer, so the sample heats up. The expected strain hardening is reduced due to the adiabatic softening, since the dissipation energy keeps the dislocations more activated than in the isothermal case. As flow curves are temperature dependent, the yield stress is decreased with increasing temperature. The adiabatic effects occurring during high strain rate testing are corrected by an empirical fitting function. This method can also be applied to the high manganese steels examined in the SFB 761.